All right, so now that everybody's here, let's start the class. So we're covering Noether's theorem and how they relate to symmetries. So this is really an important theorem, an important mathematical results for us physicists. So also I want to mention that we're close to finishing chapter 2 right now, okay? So how do conservation's law appear in the Lagrangian? And that's what is the important result due to Noether that relates conserved quantities to symmetries. In particular, Noether was probably the best mathematician of the previous century. Again, at least since we're biased because we're physicists in relation to physics, she's the one that has the best results. Okay, so you could say maybe Hilbert was better, but I don't know. In my opinion, she was better. So you guys don't have any opinions, right? Who's the better one?
No, I mean, Harmon is all the
Who? Newman?
John von Neumann.
Von Neumann? Yeah, maybe for quantum mechanics, but this spans all over. So not just quantum mechanics. So this is a beautiful thing, and let's start describing it. So we have a definition for this. So we're going to start with the function. This function is f, and it depends on some generalized coordinates, their derivatives, and a time. So this is a function of those coordinates. We're going to call this one a constant of the motion. And this constant of a motion, also known as a conserved quantity, happens if we have that this thing, this function derived by the time derivative, is given by a summation. Let's do the summation from 1 to n of this guy's plus this guy's. And then this is different from what you were seeing before. Notice that it has two little dots. All right. Questions? So that's the definition. Constant of a motion if this is true and the q's, this coordinates q's satisfy Lagrange equation. So what this means is that f remains constant. So this function f is a constant of a motion. F remains constant if when you're following the path of the system given by these q's. So this is the path of the system, right? F satisfies that, and this is the definition of the derivative with respect to time of f, right? Partials, partials, partials. And if this is true, you have a constant of a motion. All right, so let's look at the following. Let's say that different cases, right? L does not depend. So L does not depend on time. So what does that mean? Explicitly, that would mean that this thing is 0, right? So this is the first case that I want to cover. And if I have that, then what I can write is that there's a function, I'll call it h, no particular reason, and if we sum over j's, is a constant. All right. So what we have now is that h, this new function, right, is a function of qi, and in this case, function of q and a function of pi, and you guys know it because this is the Hamiltonian. And what is the Hamiltonian? Energy, right? Total energy of the system. So if you have the total energy of the system and your Lagrangian doesn't depend on time, then you know that the total energy of the system is conserved. So you guys want to see the proof of this, right? So here's the proof. So for this, I'm going to use Lagrange equation. Which is and what I'm going to do is write my, let me leave the Hamiltonian up there. So what I'm going to do is write this guy, okay? And that's going to be a summation over this j. And then I can start writing all of the terms that will go here, right? And I would have this double dot j then the first dotted j, then I need the next derivative. Is this. And this one is this. And then if for this long thing, if this Lagrange equation is to hold, you see that this time derivative is 0. If this holds, this whole thing is equal to 0. And your Hamiltonian is a constant. Okay. All right, so now I want to go into another case. And this next case is for that of an ignorable quantity. So we looked at ignorable quantities before. In this case, the idea is that you have a coordinate where your Lagrangian's derivative with respect to that is equal to 0. Then that means that for that coordinate, Qj is cyclic or ignorable. So if this happens, then this coordinate, which is defined as for your Lagrangian with respect with this Q, time derivative of Q, is conserved. Okay. So that's another case that this is true. Yeah, it would be the conjugated momentum. So this is your coordinate, conjugated coordinate, is time derivative with the partial of the Lagrangian with this time derivative is like the equivalent of momentum. So if this is x, this is px. But remember that the q's don't have to be x, y, and z. It could be whatever you want, right? Theta, more generalized. And again, for this one, you can use as proof. This one is pretty easy. And the idea is that you would take the derivative of that momentum with respect to time, and it has to be 0, right? But if you write this one out, you know that this is the time derivative of the Lagrangian. Keep trying to put G's in there. And this is equal to this. And if we go back and use Lagrange equation, which is this one right here, right? We know that this equals to this is equal to 0 for this two guys. Sorry, no dot. No dot right there. Yeah. So this minus this, or this equal to this as Lagrange equation. All right, questions? So we covered some of the cases. All right. So now let's go back to Noether's theorem. So what we need to do is the following. Consider that we have a maps, one parameter family of maps. So how many of you have taken analysis course in the math department, where you do a lot of proofs? Not many of you? All right. So this is what mathematicians would do, right? Let's assume that you have a family of maps that take this coordinate, this is the mapping, into this one, which depends on two things now. For S being any number that is a real. Okay, so what you have is that there's a map. So for instance, this is a quantity that depends on time. This is another quantity that not only depends on time, but depends on some parameter S. And that is just a real number. So for our cases, this is going to be another kind of like a time coordinate. So for this map to work, we just need to have the Q, capital Q, at S equal to 0 is going to be the same as lowercase q. So that's the map that we have in mind. If we have that map, the transformations of that map are a continuous symmetry of the Lagrangian if what we have is that this partial with respect to S of this Lagrangian that now is going to be dependent on the Q's, capital Q's, that capital Q's and time is equal to 0. So this is what Noether's theorem says. If this is true, first, you have your coordinates. Those coordinates can be mapped into another bigger set of coordinates. And if the Lagrangian is such that if you take this partial with respect to S, with this bigger coordinates embedded in that Lagrangian, then you get a conserved quantity. You have a continuous symmetry of the Lagrangian if that is true. And then for each symmetry, there is a conserved quantity. Okay. All right, so I could go over the proof, but is similar to the other things that we just did, where we're just going to use Lagrange theorem, Lagrange equation, write equations, figure out where to use Lagrange equations, and then we have a proof of this. So I'm not going to prove it to you guys. Yeah? No, it's not going to be on the exam either.
Oh. Is there anything against the continuous symmetry? What is a continuous?
All right, so I'm going to give you, instead of giving you a proof, I'm going to give you cases where this holds. And then we can discuss what is the continuous part of it, okay? So let's go over some of this, what this Noether theorem implies. So some important cases. Homogeneity of the space. All right, Vishal, what does homogeneity of a space mean? You hear that word, what do you start thinking about? What does this word mean? Homogeneity. So what does homogeneous everywhere mean? That's just a big word. What does it really mean? Same everywhere, exactly. So what we're going to do is that we're going to assume a system within particles, and they interact through a potential. So we can write the Lagrangian, pretty easy thing to do, right? Here. We have this guy, and then they're going to interact with each other based on the distance between each other, two or more particles, but they're interacting through a two-body interaction. So this interaction could be electromagnetic, gravity, van der Waals interaction, whatever you want. It just takes two bodies interacting with each other. And then what we want to look at is that this Lagrangian, so has a symmetry of translation. So what we want to do is go from this point in space, this is the mapping that we're doing, to this point in space. N is any vector. Does that make sense? So this is the transformation, the mapping that we're doing, right? These are my little q's. These are my big q's. And you see where this S is coming. If S is equal to 0, you get Ri. And whatever vector N we want, where S is again a real number. All right, so if I have that, then I can rewrite the Lagrangian and say that, you guys can do this. And see that that's true, right? So if I replace all of my Ri's up there and RJ's by this Ri translated by Sn, I should get the same thing because you're adding it and subtracting it in both ends. Yeah. Make sense? So what this is that a space is homogeneous for translation system and that this S times the vector n doesn't do anything to the equations of motions. So in mathematical terms, what we have is that Sn translations are just part of the Galilean group. So using Noether's theorem, I can conserve what is the conserved quantity associated with this translation. Yeah.
Sir, are you assuming that S into vector n is time independent?
N is any vector.
Yeah.
So
like here we haven't included that term in the time the time derivative of R.
Yeah, so that would not be Galilean invariant, right? If you had a time, if n depended on time.
Yeah. So we are considering that.
Yeah. Because otherwise you have an accelerating frame. Exactly. All right, so we use Noether theorem. We can figure out what is the conserved quantity here. So what we need to do is the following. And we have that the sum of this derivative is actually the momentum that is the thing. So what that means is that the conserved quantity is the momentum in the n direction, right? This term right here is just the momentum in the n direction, right? And that means that for all n, this is conserved. And since n was just the arbitrary vector that we decided, that just means the momentum is linear momentum is always conserved. So having homogeneity space gives you that linear momentum is conserved. So if you think about it, it means that particles don't speed up to go somewhere, right? There's no special point about this point in space for particles. They wouldn't just be here like because they are attracted or repelled or anything. There's nothing special about space.
So this is a continuous symmetry just because for any n vector.
It works.
what that continuous is.
Yep. All right, let me do a second case. So this one is similar to that one. Isotropy of space. So Katie, what does isotropy of space means?
That it's not the same theorem.
Sorry?
That it's not the same theorem.
So the other one was homogeneity, right? That is the same everywhere. So now isotropy, what does isotropy mean, the word? You're not sure? Anybody knows isotropy?
There is a preferred direction.
Preferred direction? Okay, so this is isotropy of the space. So what do you, is there something you can relate this, like how would you explain it to somebody that the isotropy of the space? Is there a preferred direction for space, or is it the same everywhere? So isotropy of the space means, does it mean the space directions are, there's no special direction in space, or the opposite? It's, no, that there's no special direction in space, right? They're all the same. That makes sense? All right. So now what we have is that, let's say that there was a vector r right here. And this vector r is going to be rotated with respect to this vector n right here. Well, it's about an axis, so I can even make it a unit vector right there. Okay? So if I rotate it, I'm going to move it in this direction by s. And that means that this guy is my shifted vector. Okay, so rotating it, that's the s direction. This is the vector. I have this vector and I rotated it this way with respect to this axis. So in a closed system that is described by a Lagrangian, the same one as before, what we need to show now that it doesn't change under rotations that take us from this r to r prime. So let's say that this is the rotation. It doesn't matter how big the rotation is. So let me just do an infinitesimal rotation. Okay. Does this make sense? It's just a tiny change, right? Infinitesimal changes. So this is the rotation I want to do. And if I do that, what that means is that r I is equal to r I plus, now I have to describe what this guy is. And it's just going to be some value times this. That's my rotation, right? This little alpha is infinitesimal. All right, so this is true. And the proof of this is that you can look, if this is an infinitesimal quantity, and I look at the length of this guy and the length of all of this guy, I'm gonna get that it's the same length. So what that means is that if this is my vector, and I rotate it to this direction through several infinitesimal operations, this length is preserved. So that's the proof of it. You can do the math for it, but that's just the proof. The length doesn't change when you do the rotation, right? And this is the direction that you chose, and there's no preferred direction that would change this. So everything is preserved when you do this to linear order in alpha. So the length of this guy and the length of this guy is going to be almost the same, except for this term right here. But that term is infinitesimal. So it's like adding a little epsilon, right? And it didn't change the length. So that's the proof. Make sense? Yes? No? So. All right, so if you have that type of translation, what does that mean? So let me go back over here. So for our conserved quantity, we make use of the theorem, and we can say that this guy and this guy are equal to, and then now we have the rotation. So we add this term. And then for the time derivative quantity, we also have this right there. So if we do this, this is the change that we have, the mapping that we did. And if we grab that Lagrangian, we get that all right, so here I try to be careful about what L and Lagrangian are. So if you look at this equation, you can rewrite it like that. And that last term right here, this guy right here, this is just describing the terms of the angular momentum. So now we see that the isotropy of space means that L, the angular momentum, is rotational invariant. And that means that angular momentum, the total angular momentum of the system is conserved. Make sense? All right. So let's go to the third case that I want to cover. Homogeneity.
So why was no time function in this event? In case two?
How come there's no time? What do you mean by time constant?
Like in previous cases, we always associate R vector and its derivative with time as well. While writing.
Oh, yeah, there's a time that, well, you don't have an actual time dependence on it, right? But you also have the time coordinate in there. You can write it in there too, explicitly. You mean, how come I don't have comma t right here, right? Yeah, I can always write it, but that's not going to change. My transformation was just going to change this one and this one to this one and this one.
So in the last one, the Ri dot vector did not change because of something, but here it changed. Why is that?
Why is this? Oh,
It's because of isotropic.
yeah. And basically now you're rotated a little bit, right? So your R dot is not the same as before because you moved it infinitesimally this way with the rotation.
But we proved that the radius, the R does not change.
Right, but it changes in position. So if I go back here, right?
Yeah.
This is R, and R dot could be pointing in this direction. And then as it rotates, r dot is now over here. So it does change in direction with the rotation with this. So it's not a specific, it's not stuck like the r dot is not stuck at the same value as before. All right, so then this is the third case I want to prove. What does homogeneity of time mean? So in math terms, it means that L, oops, of t is equal to L of t plus S. Does that make sense? So homogeneity of time means that now the mapping that we're doing doesn't affect the R's, but it's going to be, or the Q's is going to affect the T's. So in this case, we're going from T to T plus S. And for what we have, so we want a transformation that goes from T to T plus S. And what we want to say is that with this transformation, that's 0. But we actually already did this. And if this is true, then that implies that we have a Hamiltonian, right? And we have that the Hamiltonian had, and this is the summation with respect to I. And we have Q dotted with I, partial of the Lagrangian with respect to the dotted quantity minus L. And that this is conserved. So what we're saying is that this transformation tells us that energy is a constant. And we already knew that because that's the definition of the Hamiltonian, right? All right, any questions up to there?
It's equation you're using angular momentum.
No, there's no angular momentum. This is Lagrangian too, sorry. My bad. And CL. All right, so what this means is that there's a relationship between time and energy. Does that make sense? Basically, the time invariance of the system, the homogeneity of time, means that having a conserved quantity, and we found that the conserved quantity is the energy, the total energy of the system, because of this mapping, that means that the homogeneous passage of time is the reason that energy is conserved. So if we look at it from another perspective, well, what I'm saying is that time is to energy the same as space is to momentum. They have that same relationship. So when we get to special relativity, we're going to see that you have that the energy and the momentum is a 4-vector quantity. And so you have energy and momentum being a 4-vector, and you have the time and the spatial coordinates make another 4-vector, right? So that's a space-time. So you see that there's a relationship there. So what we see from here, actually, this is the most important thing, is that this 4-vector that rotates is, here we're seeing that time time plus space, we give you this 4 vector, is related to this other quantity that is the energy, and the energy with the momentum forms another 4 vectors, right? So what I'm trying to say is that what Noether came up with can be used to show that there's a link between energy, momentum, and space-time. And this exists even in classical mechanics. So you don't need to go to special relativity, but that's what Einstein did, right? To figure this out. In Newtonian physics, you can see this relationship between energy and time to space and momentum. So coming back from a conversation we were having the other day on the way out, whether somebody could have figured it out or not, I think that if Einstein doesn't show up, then 10 years later, Noether would have figured out a special relativity with this. So that's how interesting and important this is, this results of symmetry. Okay? So other things that I wanted to talk about is that when we have conservation laws, they're related through symmetries. And this is what the Noether theorem gives you. Another thing is that what are conservation laws that we know of? Electrical charge, right? How does electrical charge manifest itself? Conservation of electrical charge. Well, if you look at a neutron, how does a neutron decay? Proton and electron, right? So neutron is 0 charge, proton, electron, plus and minus 1. So if you look at other things that are conserved, you can see barium conservation number. Those are other conservation that happens. And then there's also discrete symmetries. So you were asking about discrete symmetries, right? So you can have something in nature that doesn't depend on something continuous. So for instance, we see that you can have a reflection. So if you do Ri is going to be mapped into negative Ri. That's a reflection along the axis, right? A lot of theories are invariant under this type of reflection. So if you have something that depends on a quantity and this quantity is reversed like this, there's some quantities that don't depend on it. Like for instance, if your potential depends on Ri and it was Ri 1/2 m omega squared, you can see that going from this one to this one is not going to change that potential, right? So that means that this type of symmetry is, this type of potential is invariant on the reflection. And if you have a system that is invariant on the reflection, you say that parity is conserved. So actually this type of parity conservation, which is a discrete symmetry, does not show itself in classical physics, but it shows itself in quantum mechanics. So those kind of symmetries do show up in nature. They're also discrete, and they are also in things like quantum mechanics. All right. So that's all the time I have for today. You guys have questions? All right. So